Good. All right. Hello, my name is Gabe Freedman. Today I'm going to be talking about the Rankine cycle experiment. My group of 3 will be performing that next week, and essentially the goals of this experiment is to understand the Rankine cycle, perform measurements and learn how to measure the outputs of enthalpy and temperature, pressure, and calculate all the temperature and pressure, enthalpy, entropy just from all the calculations, and to find the efficiency at the end. Next slide. So the overview of it was established by William Rankine, civil engineer, Scottish civil engineer in the 1800s. And the Rankine cycle is basically a closed loop process of extracting energy. In here, we're going to be looking at an ideal sample, basically assume no heat loss, no friction, perfectly steady state, perfectly efficient. That contradicts what we'll see in the real world, where you can't ignore friction, you can't ignore minor heat loss, but when you're running the predicted measurements, that's what you're going off of, the ideal. And for the steps of it, as you can see here, it starts off with water being pumped and work added into it, pushing the water into a steam generator. The steam generator heats up, converts water to steam. It shoots out a nozzle into a turbine, powering the turbine, and that's what generates the work that goes into the condenser, or the water that's not. The water goes into the condenser after generating the work, and it just repeats the cycle. Next slide, please. So basically 2 diagrams that help guide this experiment are the PV diagram, pressure and volume, and the TS diagram, temperature and entropy. These are basically guidelines for the ideal states. So you look from 1 to 2 over here, it maintains constant volume, or ideally it will maintain constant volume. And then 2 to 3, constant pressure. Then you move over here and you see 1 to 2, constant entropy. And then 3 to 4, it's going to be constant entropy again. So you use those as guidelines when trying to find the calculations, which we'll see later, but you use it it will be H2 minus H1, and you just you'll use these measurements to help calculate in a thermodynamic table to find those values. Next slide. So the procedure of this experiment is very long, but to summarize, I separated into 6 steps over the next 2 slides, or 6 subcategories. The first one is the pre-start, and basically you're just inspecting all the equipment, making sure it's drained, connecting all the electrical equipment like the DAC, which is basically an analog to digital converter that will just read all the measurements for us. And yeah, once you make sure the station's all clean and safe to go, you can move up to the startup, and basically just turning on all the equipment, performing a fuel leak check once it's on, just to make sure once it's running that everything's functioning properly. And then you ignite the burner and verify the pressure is rising properly. After that, you get to the preheating, and you raise the boiler pressure to 110 psi, which is around 758 kPa, or kilopascals. After it raises up to 110 psi, you open the steam or the admission valve here, actually adjust the load to 10 volts and allow the system to reach a steady state. Yeah. Once it reaches a steady state, you should try to maintain it around 110 psi, 6 amps, and 8 volts. You want to adjust the steam admission valve as needed to maintain those, but you're not going to get it perfect. But for all the predictions, that's the numbers I was going off of. And you just want to ensure that's relatively stable to move on before you move on to any of the measurements. Once trying to collect the data, measurements and data acquisition, you log the pressure using the DAC, and you'll log the pressure and temperature of the boiler, the turbine in, and the turbine out. You also will record the voltage and current output, measure the condensate volume, and record the boiler water usage. For data reduction, you want to determine the mass flow rate of it. You'll use a table that's provided in the lab manual. At the end, it's a huge table. I couldn't provide it on the PowerPoint, or it'd be too small to read everything on it. But yeah, you want to apply the steady flow energy balances. You want to calculate the boiler heat input, the turbine work rate, the generator efficiency, the condenser heat rejection, and the thermal efficiency of this. So the 3 main efficiencies that you will see in this For this lab, the only one you're really going to need to look at is thermal efficiency. However, you can also find isentropic efficiency of a pump and the efficiency of a turbine. For thermal efficiency, the efficiency is the net work over the heat in. And for the thermal efficiency, in most Rankine cycles that you'll see, like in industrial use, you want to maintain around 40%, like 30 to 40% efficiency. However, for a small model like we have, it's been said like around 15 to 20% is what you should expect. Now for the isentropic efficiency of a pump, essentially what it's measuring is like right here, just like I said, the ideal maintains constant entropy, but that's never going to happen in the real world. So it's just seeing how far it like varies from the ideal position, and same with the turbine, using like these two measurements. And then for a predicted thermal efficiency, or for some predicted calculations, I did make a few assumptions on this. So using all of that we've like already been shown, what I used as my assumptions was I assumed that like at the fourth after it leaves the condenser, or right before the condenser, it's going to maintain it's going to be a saturated vapor. And I also assume that it's going to be a saturated liquid at the start. So performing these calculations, it produced an efficiency of 16.6%, which is right in the range of what we should expect for a small model. All right, any questions?